Hello, everyone, and welcome back to another episode of the AI and Kubernetes show, the podcast where we try and explore the intersection of AI and Kubernetes. I am honored today to be joined by a very special guest, Abdel Sghiouar, who is a developer advocate at Google and also the co-host of a little podcast called the Kubernetes Podcast. Abdel, thank you so much for joining today.
Thank you for having me.
Can you tell us a little bit for our audience of Kubernetes platform engineers who are maybe, AI aware, but maybe not AI experts? Can you give us a little introduction to yourself and why you're here?
All right. If I get $1 each time I'm asked this question, I would probably
Yeah,
quit.
the tables have turned. That's right.
So Abdel, I work at Google. I've been at Google for quite a while. Developer advocate, that's my official title. Whatever developer advocate means, because it means a lot in a lot of companies. I'm an ambassador in a bunch of things. DNCF ambassador, merge forward ambassador, which is actually one of my most exciting one. It's a community that is trying to increase the diversity in the contributor space in the cloud native ecosystem. And as of recently, I am a KubeCon Co-Chair for the next 3 KubeCons, North America, Europe, and North America next year. And as you said, co-host of a podcast, and I do a bunch of things on the side, so I'm a little bit everywhere.
Wow. So if we buy you a bottle of whiskey, we get our talks accepted? Is that how it works?
I am a co-chair, so we're 3. So you probably need 3 bottles of whiskey.
Got it. Yeah. Great. Well, thank you for joining our humble podcast here. We have a lot to learn from you. One of the reasons why I thought it would be fun to have you on is, in the course of all the things that you do, but, especially in the course of the Kubernetes podcast, you have been able to interview a whole lot of interesting people at the intersection of AI and Kubernetes, whether they work at Google or elsewhere. So can you help us kind of paint the picture of this landscape? What does this look like for people who are just trying to get a handle on the fast moving world of AI, and maybe are comfortable with Kubernetes, but not comfortable with, everything else? Where do we even start? Like, how do we think about this space as a whole?
Yeah, that's a very interesting way to start. I think if people have been hearing about Kubernetes, right? They probably have heard of Kubernetes being this platform where we run apps, right? Because historically, the inspiration of Kubernetes was this thing at Google called Borg, which is basically what all of Google runs on, right? And about like 3-4 years ago, when this AI space started, I mean, AI is not new, but like this new kind of interest about large language models and AI and agents and stuff like that. The Kubernetes community was already working on supporting machine learning use cases, right? So training, fine tuning, serving. But there was an inflection point about 3 years ago where the community started looking at, and by the community, I mean the maintainers, right? Like the people maintaining Kubernetes. And this is due to 2 things. I think one of them is the industry interest, but also one of them is the companies that are contributing interest. Because the companies that are contributing to Kubernetes have an interest to make Kubernetes run AI workloads in general. So there was this inflection point where a new API started bubbling up. And so now we're going toward a direction where Kubernetes continues supporting the existing, quote unquote, call them traditional workloads. And then
Legacy non-AI workloads.
Exactly. Yeah. Legacy non-AI, yeah. And then having like first-class support specifically for AI workloads, because AI workloads have very special requirements in terms of the type of hardware they need, the kind of traffic I call that like traffic profile that they receive. And so the ecosystem now is full of first-class APIs in Kubernetes that are specifically designed to support AI type workloads, which leverages the existing Kubernetes mechanisms of like reconciliation loops and controllers and all these existing primitives, but specifically tuned or tweaked to support like more, large language models, agentic AI, etc.
And when you say, AI workloads, um, do you mean inference, like specifically, like we're running LLMs and we've got a big old GPU that we're using, or do you mean like agentic things that are maybe accessing an LLM somewhere, or what does that mean, AI work?
It's a combination of all of these. So as I said, like, fine tuning and training and even maybe serving machine learning model have existed for a while, right? It's not new. But when now we say AI workloads, I think a majority of what people mean is AI inference. So large language model inference on top of Kubernetes. And then the agentic space now, although agents are not unique in the sense that they are just like, just like a piece of code talking to a large language model, right? It's not really
Right,
that much.
right.
It's the way I look at agentic AI is it's kind of like a monolithic application running on a distributed system, right? Because when you put the agent with large language models with the tools it needs and everything that it needs to access to, it really looks like a bunch of microservices wrapped under a single entity called an agent. And you can have multiple instances of those running on the cluster. Within that ecosystem of the agent itself, there is so much traffic that you need to take care of. There is so much scalability issues that you need to take care of. And then as you zoom out, then how do you scale the agents themselves, right, across the cluster? Is also like comes up with like new challenges that we haven't seen before. So when we say AI workloads, is mainly these two things, basically, AI inference and then agentic AI.
Well, let's split that into two because I want to talk about each one individually. So let's start with inference, and I know I've got a whole bunch of questions for you because I know you gave a very interesting sounding talk at KubeCon called "Optimizing LLM Inference for the Rest of Us." But before we get into that talk, why is it, inference? My layman's view of inference is that, it it uh, it is it's a program that you run that basically takes an entire GPU or maybe consumes multiple GPUs, does a whole bunch of stuff with this GPU, and is very tied to a physical GPU, right? You're not shifting it around between GPUs because it's loading all this stuff into the GPU memory. And once you're there, you're there. So this seems like a really atypical workload, really outside of all the stuff that Kubernetes was designed for. Kubernetes was designed for like these, you know, kind of stateless, pods that could like spin up and spin down on this. Oh, this hardware dies over here, whatever. We just reschedule some ones over here, and we're doing like, these like zero downtime upgrades by like spinning up a new replica set over here, and then we delete the old replica set, and like everything just works. Now we have this very, very heavyweight thing that is like tied to the underlying hardware. Why is that happening on Kubernetes at all? Like, why not just make that, and I know it is, right? Like,
Yeah, yeah,
I know
yeah.
this is where it's happening. Why is that? Why not just do that outside of Kubernetes on a VM and like we just treat that as a special resource?
There are multiple reasons why you want to do that, and I think one of them is like the Kubernetes gives you the automation. Like if you think about it this way, like you take a large language model, you want to run it on top of virtual machine, so you need to like spin up the VM, install the drivers for your GPU, install whatever storage connectors you need, whatever hardware connectors you need, and all that stuff, and then spin up the workload, right? And I mean, on the surface, people are doing that already. I don't think that Kubernetes is the only way to do large language models. But I think what Kubernetes gives you is the automation aspect. So being able to spin up a node that already has everything ready, all the drivers it needs, all the connectors, the plugins, everything ready to go, is one of them. Then there is the resiliency aspect of Kubernetes, being able to automatically restart a workload, right? I mean, it might sound in 2026 like it's something that we have figured out. It's actually surprisingly hard to recover from failure in production in a
Mhm.
distributed system,
Yeah.
if you want to do it yourself, right? And so that's another aspect. I think that all the existing automation and scalability that Kubernetes gives you are the benefits. And now what we're trying to do is we're trying to tweak Kubernetes to support this kind of what you called atypical workloads, right? Um, and so so yeah, these workloads come with extra challenges. Like as you said, they're big, the images are heavy, the models themselves are like huge. Sometimes you might need to run them on a single GPU. Sometimes you might need to shard them across multiple GPUs on the same nodes. And in the worst cases, you might need actually to shard them across multiple nodes.
Right. Right. Yeah.
And
Yeah.
then you need high-speed RDMA connection between the nodes for, fast cache transfer and all this stuff. It's not like the way it looks at me is not we're trying to shove a workload into Kubernetes that doesn't fit Kubernetes. We're trying to leverage what Kubernetes can do and trying to make it fit those kind of workloads. That's kind of how it looks to me.
I see. Is this analogous to, like in the olden days of Kubernetes, support for stateful workloads and support for databases was like minimal, and then that had to be evolved over time. Is it like an analogous evolution?
I was about to bring that up. Yes, that's basically a pretty fair way of describing it. That where you just rethinking how to run non-stateless workloads on Kubernetes by leveraging what Kubernetes can do and just making it do it better. So it's basically doing databases again, all over again, right?
Okay. All right. So that makes sense. And that's inference. And we're going to get back to that topic. But like the other thing you mentioned was agentic workloads. So now we have something that is not these big, bulky, inference workloads. They're not even necessarily, they don't know anything about GPUs. They're just talking to, right? They're talking to inference like over some HTTP connection that lives somewhere. What is unique or interesting about those workloads? You mentioned they were analogous to microservices and there's lots of communication. What does that look like? What is that communication, and how are they different? Other than the fact that they're like talking to an LLM, are they different in any other way from like a non-agentic application that talks to some service over here over HTTP?
Yeah. So it took me some time to think about this, and I believe I was probably one of the first people to write an article about it, about like agentic workloads on Kubernetes, and to spend some time kind of reflecting on it. So there is a few things. So what's an agent? An agent is an application talking to a large language model, which has access to tools and MCP servers, and I call that functions, right? Like whatever, a tool, an MCP server, a skill, it's just a function, right? There are a few things. One of them is the fact that you have all these network flows. So the agent to the LLM, the agent to the tool itself could be a built-in tool inside the agent code, or it could be calling an external endpoint, right? Again, whether that's like an MCP server or tool, or whatever that thing is, right? Then you have the memory management, because agent needs memory so it can keep context over time. Then you might require storage, but I mean storage is not it ain't special, but it's just like the sheer amount of network traffic within the agent container or pod is very different than a standard, let's say, backend application where your calls are predictable, your traffic is predictable, you know exactly which flows that thing will perform. And then the other aspect is that agents are undeterministic, because the large language model is undeterministic. So what if somehow somebody prompts the agent and the agent decides to just call an external endpoint that you haven't planned that it would exist in the first place, right? So it's this kind of like very tiny quirkiness of agents that makes them special. So there are a few things that I've been thinking about actually over time. And I mean, granted, I don't have the solutions to all of them. Like one of them for me is when you have an agent that calls a tool that performs an action, that tool is a separate process. And if that tool process executes within the agent container, so how do we do resource management for the agent container itself, right? And what if that tool process is loading data from a database and ends up loading terabytes of data into memory, right? That's one of them. The second one would be managing identities, right? Like, so how do you get the agent itself to call an external endpoint through an MCP server, but using either the identity of the agent or the identity of the user prompting the agent? And the funny thing about all of this is at the bottom of all of this is just very basic stuff. Like it's auth-n, auth-z,
Right.
a policy
Right.
management. So it just like, it's so complex when you look at it from how these interactions happen within the agent itself, that it might require extra, and I'm putting quotes on quotes, like extra care, I would say, for
I see.
security, authorization, authentication, resource management, etc.
Yeah. Yeah. Certainly it seems to me, and again, this is kind of the beginner's perspective, but the fundamental behavior being non-deterministic means that you have to suddenly take a very different approach to certainly to security,
Yeah,
right? Like, it seems
yeah,
like at some point this thing is going to find the delete your database endpoint and it's going to call it, and like it's just a matter of time, right? Whereas you didn't
exactly.
really have that with code that has been written and reviewed by humans. And then, yeah, maybe wildly different or unpredictable resource usage, whether that's communication or something else.
And there is
Yeah.
actually, so I was at Next last week, and we had like a Kubernetes meetup, and I had like one very, very specific conversation that I've never really thought about. This was the first time somebody brings it up. So the person that I talked to said, okay, I run agents in Kubernetes, and I'm calling so they run on Google Cloud, but they are calling a non-Google Cloud LLM. So they're talking to Anthropic or ChatGPT, right? So how do I manage your traffic? How do I make sure that if the call fails, it can automatically retry? And how do we take care of the latency? And I was thinking about it. I was like, well, this is maybe something neither us, neither OpenAI have really thought about, right? And the reason why these things, so somebody might listen to this and say, like, I mean, who cares? Like, you call an external endpoint, it's just an HTTP endpoint. But no, because when you're calling an LLM, you are sending potentially megabytes of content, right? Think about like a coding agent. You might be shipping an entire code base to the large language model across an HTTP request. This is not standard web traffic. It's large language model traffic, which includes potentially very large prompts, maybe multimodal type prompts. So it could be pictures or videos. And then the request could take forever to come back. And then when it comes back, the return could be also potentially megabytes of content. So it's just, I think it's like the sheer volume of communication between an agent and a large language model makes it very different than a standard web application, right?
Yeah. Yeah. Okay. Okay. That makes sense to me. Really interesting. Um, okay, well let's go back to inference for a little bit because I'm really interested in this talk that you gave at KubeCon, and this was in Amsterdam, right, just a few months ago, called "Optimizing LLM Inference for the Rest of Us." So what was kind of the point of this talk? Like, why do we care about optimizing inference? Well, I think I have a guess, but like maybe you can explain why optimizing inference is important and why it's maybe more important than optimizing other things. Um, and why the rest of us? Who is this talk aimed at? Is it the underground?
Yeah, pretty much. So the whole point of this talk was from myself and Mofi Rahman with my colleagues, thinking about. So we work for Google. So technically, we potentially have unlimited access to resources. Now, what if you're not Google, right? What if you are not, Google or AWS? So when you're on a super cloud, and what if you don't have unlimited access to GPUs? How do we deal with like optimizing the inference for large language models using open source because the thing with Kubernetes itself is that Kubernetes is the open source project, but GKE is Kubernetes plus plus and EKS is Kubernetes plus plus, right? It's all of these managed solutions have extra proprietary potentially integrations that you might not have access to if you're just in the open source space. So what we did is we really went and looked at all the optimization we have done on GKE for large language models, and we looked at open source equivalents. And we started looking at, okay, so let's say we have some feature called image streaming here. So image streaming is like fast download of the container image on the node when the pod has to be spun up. How do we achieve that in open source space? Do we attach a file system with all the containers cached on the cluster? Do we use Docker images as a volume? Stuff like that, right? How do we optimize access to the underlying GPUs without the automation that a managed platform gives you, right? So that was kind of the core of the talk. And we started exploring it from there. And then we expanded into looking to like what are the different optimizations, and we realized very quickly that actually it's a very deep rabbit hole that we can go into because tooling is endless in this space. So what we ended up, if people who are listening to this watch the talk, we ended up basically just saying, okay, we have a large language model running inside a serving engine running inside a pod. That's 3 layers. right? So that there is accelerators at the bottom. There is the serving engine itself, VLLM or Olama or whatever that can be, which needs access to storage and needs access to network and stuff like that. And there is the model itself. So we split it into these layers, and then we talked about the optimizations as each layer. So network, storage, caching, resource management, so accelerators access. And then we looked also at so that's like a vertical kind of optimization. And then we looked at horizontal acceleration. So how do you auto scale your like your pods? So how do we actually go about even setting up auto scaling? Because Kubernetes does already have very good auto scaling mechanisms with like horizontal pod autoscalers, vertical pod autoscalers, which you can plug to some custom metrics, and then boom, you have more requests coming in your queue, you auto scale your workload. But with LLM traffic, that's not how it looks like. Auto scaling is done on other type of metrics, like how busy are your accelerators? How busy are the large language models in themselves? So, aka how much processing or
Yeah.
how long is the queue they're waiting to process?
Hmm.
So we started looking at these things. So it's like 3 or 4 layers of vertical optimizations, and then few layers of like horizontal auto scaling optimizations. And we sort of like packaged it. For the rest of us, the idea is like, if you don't have deep pockets and endless GPUs, how do we approach this, right?
And was this was using open weight models as
Yeah,
well?
this is all using open weights model, correct? Yeah.
Do you do you I have kind of a side question. I apologize for grilling you. This is not
Of
supposed
course,
to
of
be
course.
an interrogation. So like,
I'm
you
enjoying
know,
this.
uh, uh, do you, so I've been following some of the open weight models with a lot of interest. The research that I've read suggests that they are trailing state of the art, proprietary models by like 3 months at most. So like the gap between the quality you're getting from something like Gemma 4 and like what you can get from, the full bells and whistles Anthropic or OpenAI is actually quite small, much smaller than I expected, the gap in quality. Do you think that's going to continue? Like why are Google and other companies making these open weight models? What's in it for them? Because they're also trying to sell inference with like the proprietary stuff.
I mean,
Is that going to continue?
the very honest answer is simply that you capture the market of people who want to use the SaaS hosted models by releasing Gemini and Claude and Opus and all these models, and then you also capture the market of people who doesn't want to use those by making open weight model available and then optimizing your infrastructure to run them.
I see.
Right.
Okay.
So that's essentially that's, I would say, the very direct answer. Um, Now that would be how maybe super clouds would approach this, right? But if we look at somebody like I mean, you said, okay, open models are trailing the big models. I think that there is actually other open weight models that are even ahead, like Kimi 2.6, right? It's ahead in terms of coding. Like when you did the benchmark suite, it's ahead of all the other models, right?
Oh,
Um,
that's interesting.
yeah, it is. And
Yeah.
the 2.6 just came up like very recently, and um, that I think that the business model there is that there is Moonshot AI, and they just host the model for you. So they are making it available as open weights, but like yeah, it is open weights, but not everybody can run it. I mean, like a Kimi 2.6 needs like 256 gigabytes of NVRAM. Like, who has that?
Okay.
Right? So
Yeah.
so, and then I would say maybe the other reason is that like those large language models that are cloud hosted, they're not always good for all the tasks, right? So like they're good for certain things, but they might suck in like very specific tasks, or actually you might even not need them if your task is very small. So sometimes it's actually more cost efficient to run your own small large language model to do very specific uh, tasks instead of talking to Gemini or talking to Claude or whatever, right?
That's really interesting. All right. Okay. So that answers a lot of that. Now, what about kind of the set of projects in this space? When I was walking around KubeCon, I saw Well, obviously, like every project had like some AI kind of like component to
Of
it, but
course.
it seemed like there were a whole set of interesting projects, K-serve and LLMD, and then there were like conformance projects and things. If you're kind of trying to get a handle on this space, how do you think about this whole set of projects? Are there things we really need to pay attention to? Is this a very early ecosystem it's all going to develop? Like how much do we need to like to to learn about what's out there?
Yeah, there is I saw an infographic recently on Twitter that I would send it to you. Maybe you can add it to show notes. That has like a very good kind of diagram showing where all these projects kind of sit on the stack, right? The thing is, all these projects are trying to solve one particular problem at a very specific layer of the stack, right? So the examples you mentioned, K-serve, that's just serving, right? So it's just inference done the Kubernetes way. So you have CRDs and you manage your serving using Kubernetes way. LLMD is trying to solve the networking layer. So what LLMD is, it's basically a set of architectural patterns. They call them well-lit paths. I call them architectural patterns for doing a very specific serving on very specific type of hardware for very specific type of models. And when I say type of models, I don't mean very particular model like Gemma or Llama. It's like so let's say an MOE, a mixture of experts. How do we do serving for an MOE model on top of GPUs, right? And then how do we plug that to the networking layer? So how do we do all the stuff I've been talking about, like autoscaling based on network traffic, which again doesn't look like regular web traffic. It's uneven requests. Some are small, some are big, etc. I mean, some of this. I will give you a very, very particular, very, very specific example, which is mind blowing to me. Um, So for some reason, all these serving engines like Olama and VLLM and Triton and all these open source serving engines, right? They have all decided to standardize around the OpenAI spec, which is an API spec that was released by OpenAI, right? And this OpenAI spec has basically you have a path and then you have a JSON payload, and
This
the
is the
path.
thing with like V1 chat
Correct. V1 chat
completions.
completions,
Yeah,
right?
yeah.
Good. But then if you want to call it, what you have to do is you have to pass the model ID in the JSON request, in the body of the model. Like 99% of load balancers cannot actually load balance based on the body of the request. They mostly load balance on the path, right? So the open source community had to create an extension for the Gateway API called the Gateway API Inference Extension, which had basically a router, which is a pod that sits in your cluster, where the load balancer gets the request, send it to that router, and that router will be configured to extract the model ID and know exactly which pods can serve that particular model ID.
Was that just to handle that one choice of putting this routing in the
That was the first
in the header?
implementation. So they made it generic. They called it the endpoint picker, where the endpoint picker, which is this router, can pick the endpoint. I mean, hence the name. But they made it initially. The first implementation was like the routing based on the model ID. But the idea that eventually you can also make it route based on metrics. So if that endpoint picker is aware of the metrics of the underlying pods, the backends, then it can also route based on that. And then the next step would be, how do you actually do prioritization based routing? So how do you route based on which traffic is more important for your business, right? So that's why I mentioned in the beginning. It's essentially taking Kubernetes and making it support this like very specific quirkiness of large language models, which doesn't exist in web traffic, right? So that's just one example. And that's what LLMD, by the way, is based on this inference extension, but it adds extra routing logic with extra policies, which can do routing based on queue size, for example. So how busy is a backend? By the way, one thing to mention for people to understand why I mentioned queue size a couple of times, large language models are surprisingly serial in the way they process requests, right? A lot of them does batching. So they will batch a bunch of requests and then process them in one go, which means if the model is busy processing a batch of requests, everything else will be queued and waiting for the model to finish, right? Which means that the size of that queue matters, because if you keep queuing more requests on the same pod, you have more latency, right? So being able to route based on the queue size is important. And So yeah, that's what LLMD does, and it has some extra features, but that's like kind of the base, the in a nutshell what it is.
Yeah, got it. Okay, so lots of stuff is being developed then still, like to handle to handle all the intricacies of serving inference at scale.
Pretty much, yeah.
You also gave a talk in the previous KubeCon titled "Yes, you can run LLMs on Kubernetes," and that was like a year earlier. How much change was there, just in the span of that year between the things you were talking about and kind of the state of inference on Kubernetes?
Quite a lot, actually. I would say when we built that talk called "Yes, you can run LLMs on Kubernetes," we really did not, like, LLMD didn't exist or was barely like version 0.1. Um, there was like all these like volumes as images or images as volumes, which is Kubernetes eventually implemented, adding an image, a volume to the pod, which is pointing to a container image. Things like um, I'm forgetting like projects, but like the AI conformance project that you talked about, it didn't exist back in 2025. So just between 2025 and 2026, all these projects have happened, and like eventually they got open source, and then some of them became part of the CNCF, etc. One funny thing. So the talk you mentioned, yes, you can run LLMs on Kubernetes, was obviously like a provocative title because you're competing for attention when you go to a
Yeah,
conference.
yeah, of
So
course.
that was
Yeah,
the goal.
yeah.
And eventually, that was like early 2025. Then I discovered LLMD. I started like looking into it. I started testing it and playing with it. And I submitted a talk to a conference in Belgium, which happened end of last year, called DevOps Belgium. And it was a deep dive, a 3 hours deep dive into LLMD. So it's like really 3 hours where I'm just really going deep. It's one of the most unique conferences that has this concept of deep dives, right? And I spent like months preparing for it. And the more I went down the rabbit hole, the more I realized, wait, like there's so many jargon that if I don't explain, people will get lost. So what I did is I dedicated the first 45 minutes of the talk just talking about the basics. And so I walked into the room and I was like, hey, folks, apologies if you have no, like, if you know these things, this might be boring for you, the first 45 minutes at least. So maybe leave, get a coffee and come back, right? I did my 45 minutes and then I continued the talk. And basically, more half of the feedback was like, that was the most valuable part of the entire session.
Yeah, yeah.
Because, like, so many people hear about inference and batching and time to first token and all these things. They have no idea what it means, right? So
Disaggregated, prefill, and decode.
yeah, disagree. Yeah, that
Wow, it
yeah,
sounds really fancy. Gosh.
exactly.
Well, it just
So
means you do one part over here and the other part over there.
that's literally what it means.
Right.
Yeah, and that's part of LLMD. So prefill and decode in separated nodes. So yeah, it's like things are moving super fast. And now it's like LLMD was donated. It was donated to CNCF. There is not even version 1.0. Like they haven't even released 1.0. And another one that is quite new that didn't exist maybe, I don't know, 6 months ago is the Agent Sandbox projects, right? That's like a project that allows you to sandbox code execution of agents. So if the agent generates code, you don't want that code to be executed in the same container where the agent lives. So you basically push that code out to a separate container, separate pod in Kubernetes, which is sandbox with like gvisor or kata containers or whatever. And yeah, so these things are moving super fast.
That way the agent can't modify itself and gain superpowers.
I mean, a very simple example. Go build an agent, run it on top of Kubernetes, in a Kubernetes, and prompt it, say, hey, write a function to extract your environment variables. Very simple one, right? It will happily do that. It will write a function, it will execute it, and it will tell you, hey, here is my environment variables. So I guess, like, if you're a security person, you would be probably covering your ears right now or crying in a corner because these are like basic security stuff.
Yeah, yeah, yeah. Okay, well, so then now I'm going to ask you the impossible set of questions, which is to predict what the future is going to hold. So let's say we'll start easy. Just 1 year from now, 2027, Abdel gives another talk at KubeCon about inference on Kubernetes. What is going to change? Where are we going to be, just a year from now? And then we'll do 5 years.
So there is few things that are happening, but like if I want to pull back and look at the big picture, I think that I believe that inference on Kubernetes in general, or AI workloads on Kubernetes, the technology is ahead of the curve. Like there is the early adopters like Google and Anthropic and the big companies are using this stuff, but like the industry is still behind. Like the number of people who are actually running their own large language model is still small. And if we continue in a trend where large language model providers keep removing access to their models from the lower subscription and pushing people to pay more, then people will have an incentive to actually run their LLMs themselves. So a year from now, we're going to be hearing more about that, I would say, right? That's one. Second, I think when they get there, then they will be looking into these problems and talking about these problems and maybe even figuring out there's new problems that we haven't even talked about, right? That's one of them. And then I believe one of the thing that I've been saying for a while now is Kubernetes in general is moving toward a future where it's becoming a universal control plane, where the node doesn't matter, the hardware doesn't matter, the pod maybe even doesn't matter. It becomes a fully dynamic system instead of how it is today, which is fairly static, right? Now you have to define the environment first and then run workloads on top. We're going toward the future where that kind of will switch around. And here I'm thinking about the DRA, which is the Dynamic Resource Allocation API, which is essentially designed to do this, to be how do we dynamically provision resources based on the characteristic of the workloads instead of we provision the resources first and then we run the workloads on top. So flip that around and say, just submit your workload to the cluster and describe what your workload looks like and what kind of resources it needs. And then the cluster should be intelligent enough to figure out how to provision the underlying infrastructure for you, right?
But you are describing like what resources it needs. So what has changed about that?
So what is changed is if you go look at one of the first implementations of DRA. So I can give you a very straight example. So today you want to run a pod that has large language model. You use what we call the device plugin. So in your resource definition, you say, give me this number of GPUs with this particular type of GPUs, like A100. Your cluster will have a couple of nodes that has A100. The scheduler will do a very fairly simple scheduling task, right? Resource available, blah, boom, match pod to workload, right? What DRA allows you to do, for example, is it allows you to, it has two aspects. There is the platform admin aspect, and then there is the user aspect, right? So the platform admin will describe the capabilities of the cluster. It will say, hey, I have my cluster with GPUs that has this amount of memory, this amount of cores. And then the developer will say, deploy this workload on a node that matches this amount of memory, this amount of cores. I don't really care about the model, right? Model is not a problem. So that's the dynamic aspect. So if you think about it, it's a bit like what the storage API have been trying to solve for a while, which is you create the storage class, which describe the storage characteristics. And then the pod claims the class via description of which class it needs to match to, right? As far as you're concerned as a user, you don't care that, I mean, you don't really care that the cluster, that the underlying disks are Western Digital or Seagate or whatever, like, right? So think about that, but take it up a notch with hardware accelerators, with networking, with even maybe even security, right? So you know what I mean? Like that's kind of the philosophy, I would say.
Okay, interesting. All right, so we've got that in the future. That's 1 year in the future.
That's 1 year, yes.
Okay. All right, now take us 5 years into the future. Humanity is it still around?
That's a very good question. I was about to say, if we're still around in 5 years,
Yeah.
I would say that like one thing that is clear is that the sheer size of clusters is like going through the roof, right?
Yeah.
Like it seems like all the cloud providers are now in some sort of race to who can run the biggest clusters. And that's actually coming with some fundamentally different architectural decisions about how the cluster itself runs.
Is that driven by AI or is this like independent?
I think this has been happening before AI, simply because running fairly large clusters is much easier to manage than like very big number of small clusters for most companies, right? Think of you like a big company that does whatever, and then you have a dedicated platform team. They much rather run one large production cluster for everyone than run multiple small production clusters for for individual teams. And so take this and then 10x it, right? So how do we go from, I mean, we can talking about numbers. Kubernetes initially supported what, like 1,000, then it went to 5,000, then now the open source is 15K, then Google can do 135, just can do 130. Azure at some point is going to come up with some other crazy number. Like it's pushing the boundaries of what the cluster looks like itself in terms of the size. As I said, that comes with fundamentally different architecture decisions. So no more etcd. Maybe your control plane is stateless. Maybe the control plane even doesn't run in the same region where the cluster is. Like, it doesn't really matter. You know what I mean? So that's one of them. I think that boundary will keep being pushed. Then I think that probably some fundamental new stuff for the networking aspects, because so far we've been running with this model, which is a pod have a single interface, maybe two if you're lucky, right? So what if in the future it has 5? Because an agent might need one interface to talk to a large language model, one interface to answer user responses, and one interface to talk to tools. And then if you segregate this into 3 interfaces, that makes it easier to secure, right? That could be a very basic example. And then if I want to bring your company into the picture, I think that the future might also look like service mesh capabilities becoming natively available within Kubernetes instead of having to have an extra tool, right? Like the service mesh is, for me, is a very cool tool. Like it's the promise of service mesh to do intelligence in the wire is amazing, but having to install extra tools just to implement the certain functionalities sometimes kind of be a friction for some companies or some teams. So what if we make these things like natively available inside the cluster itself or inside Kubernetes itself? I mean, I'm not talking about the very advanced features. It could be just like end-to-end encryption, very very simple, right?
Mhm,
End-to-end
mhm,
MTLS, right?
mhm.
So yeah, I think that these are probably kind of some of the. I'm not that much of a visionary, but that's kind of how I look at it.
Yeah. 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 Okay. Great. No, that's a very optimistic view of the future. Thank you.
Yeah. And if I might just add 2 things that just like
Yeah.
for fun, I think that regardless of how the future looks like, there will be fundamentally still 2 problems we have to solve. One is DNS, because it's always
Uh-huh.
DNS, right?
Uh-huh.
And one
Uh-huh.
of them is IPv4. I mean,
Oh,
it was
okay.
supposed to be the year of IPv6 10 years ago, right?
Uh-huh. Uh-huh.
So
Yeah.
I'm not optimistic about these 2.
Yeah. Yeah. Right. Okay. So good. We'll still be able to complain about DNS, as the robots are are hitting us to work faster. Yeah.
Exactly.
Yeah,
Exactly.
wonderful. Abdul, thank you so much for your time today. I had a great conversation with you, so really appreciate all of your knowledge and insight that you shared with us.
Thank you so much. Thanks for having me.
All right, and let's do it again sometime.
Of course, anytime.